Hello everyone, welcome to lesson 6 in the fluids chapter. In this lesson we're going to change things up a little bit and we're going to talk about fluids in motion. For the previous 5 lessons of the chapter, we've always looked at fluids that are stationary and the pressure that's involved with them and when things can sink and float and buoyant force. But here we're going to set the fluids in motion. Our objectives are to talk about something called the flow rate of a fluid and then do some flow rate calculations and finally end things up with something called Bernoulli's principle. So to get things started, I actually wanted you to try a question, and the question is this. Water flows through section A of a pipe, so we have this pipe here and water's going through it. Let's see, water's flowing through the pipe and it has a velocity of v. When the water moves into section B of the pipe, its velocity will A, increase, B, decrease, C, remain constant, or D, there's not enough information to determine. I want to see what you put, and so try to pause the video, and when you come back, we'll talk about what the right answer is and why. Okay, so hopefully you were able to pause the video and take a guess. I know that we haven't gone through it yet, but I wanted to see what you put. And if you put that the velocity will increase, then you were correct. So the first thing that we're going to talk about with what we call flow rate of a liquid, or the speed at which it moves through something, is that it depends upon the area that it's going through. Because fluids are incompressible, when we place them in a smaller area, and when I say area, I mean a cross-sectional area, when we place them in a smaller pipe, they end up going faster. We have an equation that describes how this flow rate changes with area, and it's called the continuity equation, and it looks like this. Area 1 times velocity 1 equals area 2 times velocity 2. And the area is just the cross-sectional area of the pipe, and the velocity is the speed with which the liquid is moving through that pipe. I'd like to do an example of that with you to show you how it works. And here's our example. It says water moves through a pipe with an area of 2 meters squared at a velocity of 5 meters per second. If it then passes into a pipe with an area of 0.8 meters squared, what is the velocity of the water in this intersection? So first we'll read through this again and pick out our key information. So one pipe, the first pipe, has an area of 2 meters squared, and the velocity of the liquid in that is 5 meters per second. The second pipe, the new pipe, has an area of 0.8 meters squared, and we want to find the second velocity. So right away we can see that the area is going down, which hints us to the fact that the velocity should go up. But let's double check it with the continuity equation. Area 1 times velocity 1 equals area 2 times velocity 2. To solve for velocity 2, I'm going to divide both sides by area 2. And I'm going to get a final equation of area 1 times velocity 1 divided by area 2. And now I'm going to plug in the numbers. So area 1 is 2 meters and velocity 1 is 5. And then we're going to divide that by 0.8. And velocity 2 is going to equal, let's see here, do it on my calculator, 12.5 meters per second. So you can see that as we predicted, the velocity is going to increase. And if you just think of a practical example of this for a second, if you've ever had a garden hose and water is coming out of the garden hose, if you put your thumb over the end and decrease the area of that opening, the water really increases in velocity and shoots out much farther. So that's a practical example of flow that really depends upon the area. Continuing with that idea of velocity and area of a moving liquid, we have something called Bernoulli's principle. And Bernoulli's principle says that as the velocity of a fluid increases, the pressure within that fluid decreases. So fast-moving fluids generate low pressure, and slow-moving fluids generate high pressure. The image that I have on the screen shows a large area pipe, and we get a large area pipe with a low velocity, and we get a high pressure. When the liquid goes into the smaller area region, the velocity increases, so the pressure actually decreases. And then when it goes back into the higher area pipe again, the velocity decreases, which means the pressure increases. Bernoulli's principle, if we take this fact that the velocity increases and the pressure decreases, has some nice practical examples that explain some of the things in the world around us. And the two that I wanted to point out to you are air going over a wing. And even though air is not a liquid, it behaves in form of gas. Bernoulli's principle still applies. That when air passes over a wing, the wing is shaped such that the curve on the top makes the air that goes over the top of the wing travel a greater distance, so it has to move at a higher velocity, which means it's a lower pressure. The air on the bottom doesn't have as great of a distance to travel, so it's a higher pressure. And the pressure differential causes what we know as lift. It causes the plane to get some lift. The other practical example of this is if you've ever seen like a baseball game or a ball or in any sport curving objects usually have a spin to it. And what happens with that spin is that when the object spins, it runs into the air and it slows the air down on the side that is spinning into the air. So this is a low velocity of air, which means it's a high pressure. And on the side where the spin is moving with the air, we get a higher velocity, which means we get a lower pressure. And that pressure differential causes a force that causes the ball to curve. So a very simple explanation of a curved ball. It has to do with, in part, Bernoulli's principle. So to wrap things up for this last lesson of fluids in motion, fluids increase velocity when they are forced into smaller cross-sectional areas. The continuity equation shows us how we can calculate the differences in velocity when we know the differences in the area. That's A1 times V1 equals A2 times V2. And Bernoulli's principle tells us that as we increase the velocity of a fluid, decrease the pressure of that fluid. This is the final lesson in our fluids chapter, so to complete this, you should do the lesson 6 quiz on the Google Forms, and I hope you enjoyed this lesson on fluids in motion and this chapter on fluids. Thanks.